So we're going to cover one section from Chapter 20. And then if you take Chem 1B, you'll get to cover it again later. So this is continuing the idea of oxidation-reduction reactions, but it's a method for balancing them. So just a reminder, oxidation is loss of electrons, reduction is gain of electrons. Oxidation is an increase in oxidation state. Reduction is a decrease in oxidation state. So when we have an oxidation-reduction reaction, we have to be able to balance the equation, and it's not always as straightforward as balancing a non-redox reaction. So the masses have to the masses have to balance, meaning if I have one calcium atom here, I have to have one calcium atom there. But we also have to have the charge balance. And that sometimes is not apparent because this one doesn't look like it has any charges. But we have to make sure that if something's losing 5 electrons, there's some other things that are gaining 5 electrons and that we don't leave electrons unaccounted for. So the half reaction method says, well, let's break the equation into 2 half reactions, one for oxidation and one for reduction. We're going to balance those individually and then add them back together. So this can happen in an acidic solution or a basic solution. So we'll learn how to do it in an acidic solution first. And these are the instructions from your textbook. It says assign oxidation states. We actually don't really have to do that part. So you can kind of skip that. So we'll start by separating the overall reaction into 2 half reactions. And then when we balance each of the half reactions, we're going to do it in this order. We're first going to balance with respect to mass, meaning the numbers of atoms. And we're going to balance everything besides hydrogen and oxygen first. Then we'll balance oxygen by adding water and balance hydrogen by adding H+. These reactions are occurring in an acidic solution. It's aqueous, so there's plenty of water around, so we can add water wherever we need to balance the equation. And it's acidic, and so there's also hydrogen ions present. After we do that, we're going to look at the 2 half reactions and balance each of them with respect to charge. So make sure that the charge on the product side and the reactant side is the same. So we'll end up adding electrons to one side on the reactant side and one on the product side, because one's an oxidation, one's a reduction. So when we get that straightened out, now what we need to do is we'll need to add these 2 half reactions together, and we'll want the number of electrons to be equal. So we may have to multiply one or both of the reactions by a number, and then we'll add them together, cross out extra stuff, and check it. Okay? And if that didn't really make much sense, that's okay. So on this first example, I've made some sort of crib notes over here so that we can remember what we're doing here. So we're supposed to balance this redox reaction in acidic solution. And this is a really easy one, but it's a good one to practice doing the steps on. And again, I'm going to say, well, we don't really have to do this part. So I'm going to separate this into 2 half reactions. So the ones we're going to see in Chem 1A are going to be relatively simple. Typically, you'll have 2 reactants and 2 or more products. And so one of the reactants will be in the reduction reaction and one in the oxidation. And we don't even have to identify which is which. I'm just going to separate this apart. And so I want to have the H+ as a reactant. And then one of these is going to be the product. Well, can H+ turn into chromium? Nah, it's probably going to turn into H2, right? And then the other part of this is the chromium atom turning into chromium ion. Could that happen? Yeah, just with some electrons moving around, right? And that's what this is all about. So we've got chromium going to chromium 2+ ions. That's step number 2. Separate into 2 half reactions. And just pick the reactant and product that look most alike to put in one reaction and put the others in the other reaction. So now we balance with respect to mass. So this is like the regular kind of balancing. So I look at this and I have one H here and I have two H's there. So if I put a 2 over here, then I'll have 2 hydrogens on each side. Okay? And here I have 1 chromium and 1 chromium. That one's already balanced, right? So we do it in order other elements, oxygen and then hydrogen. We didn't really have to worry about those orders for this simple example. Now we're going to balance each half reaction with respect to charge. So if we look at this first one, here in the reactant side, I have a total of a +2 charge. And on the product side, I have a total of 0 charge. So it seems like 2 electrons appeared out of nowhere, right? That can't happen. So I need to balance the charges on the equation, and I do that by adding electrons. I can add electrons to the product side, or I can add electrons to the reactant side. Either way. So for this one, if I add 2 electrons to the reactant side, I've got 2 plus charges here and 2 negative charges. The total charge of the reactants is 0, and the total charge of the products is 0. This is the reduction reaction because I'm gaining electrons. Reduction is gain of electrons. So this is gaining electrons. It's the reduction half reaction. Then down here I've got a total of 0 charge on the left and +2 on the right. So I'm going to add electrons to get them the same. Sometimes they're 0 on both sides, but other times it might be +2 on both sides. They just need to be the same. And all I can do to balance it is add electrons. So down here, I'm going to have to add 2 electrons to the product side. So +2 charge. Come on screen, there you go. +2 charge and 2 -1 charges, total of 0. Total of 0. Okay? So that's step 4. Step 5, make the number of electrons equal. Well, this one has 2 electrons and that one has 2 electrons, so that one worked itself out. Step 6, add the half reactions together. So what I'm going to do now is I'm going to add these 2 back together. And before I add them, I'm going to look and see, are there any things that look like spectators? They appear as reactants and products the same. The electrons? Here I have 2 electrons in the reactants and 2 electrons in the products. So the electrons are always going to go away because we set it up that way. So the electrons are essentially canceling each other out, and then I'm just going to copy down the rest of the stuff. So 2H plus aqueous plus Cr solid, making H2 gas plus Cr2 plus aqueous. And then we should verify. Go through and make sure total charge is +2 over here, total charge is +2, 2 hydrogens, 1 chromium is balanced. Any questions? This is a reaction that we could have balanced by inspection and it would have come out just fine. But I'm just using it as an illustration of how to do the process.
When you were adding the electrons, how do you know which side?
When I was adding the electrons, how did I know which side? For each of the half reactions, I'm looking at it separately and I'm trying to make the charges of the products, the reactants, and the charges of the products be equal. And so before I put the electrons in here, I had +2 and 0. And so how can I make them the same? And the only thing I can do is add negative charges. So that tells me I have to add 2 electrons here. Good question. Anybody else? Let's do another one. So balance this reaction in acidic solution. So the first thing I'm going to do is I'm going to break this into two half reactions. And I see that I have Fe2 plus here and Fe3 plus there. Those are really similar, so I'm going to put those in one reaction. And the MnO4 and the Mn2 plus are going to go in the other one. So I've got Fe2 plus aqueous, making Fe3 plus aqueous. And then the other one is the MnO4 minus aqueous and Mn2 plus aqueous. The Fe2 plus became the Fe3 plus, right? So I'm putting those together. And the MnO4 minus became the Mn2 plus. Those are similar. There's no way I can take iron 2 and make it turn into manganese 2. That just can't happen. So I made my half reactions, and now I'm going to balance them. I'm going to balance for mass first. So my first one, I have one iron atom and one iron atom. It's already balanced. The second one, now I've got manganese and oxygen. I'm going to do everything but hydrogen and oxygen first. So that's the manganese. So here's one manganese and one manganese, so that's already balanced. Now, there isn't any hydrogen to mess around with, but I have oxygens. How do I balance the oxygen? I have to add water. There's no oxygen on this side, right? We're like, but it's an aqueous solution. There is water around. So I have 4 oxygens over here, and so I'm going to add 4 water molecules so that I get the 4 oxygens. Just because that's what the directions tell me to do. So I balanced the oxygens, but I introduced another problem. Now I've got a hydrogen problem. I balanced the oxygens by adding water. I balanced the hydrogens by adding H+. So I have 4 times 2. I have 4 hydrogen atoms over here times 2. Almost screwed that up. 8. I have 8 over here. So then over on this other side, I'm going to add 8 hydrogen ions. Those are things that were not present in the original equation. And this is why if I gave you this equation and said balance it, you'd have a hard time because you can't just put coefficients because there's no oxygen in the products. But there's water. So in these redox reactions, sometimes water is formed and water is destroyed, and so we can't necessarily see that just from looking at the original unbalanced equation. So balanced for mass. Any questions about that? Now I'm going to balance for charge. So in this half reaction, I have a +2 on this side and a +3 on that side. I need them to be the same. So if I add 1 electron to the product side, I've got a +3 and a -1. Now I have a total of +2 on that side and a total of +2 on this side. They're equal. They're not 0, but I just need them to be equal. Then the bottom one is a little messier. So over here on the product side, I have a total of a +2 charge. And over here on the reactant side, I have +8 and a -1. So I've got +2 and I've got +7, right? I need them to be the same. And all I can do is add negatives. So I can add 5 electrons to this side and bring this total down to +2. So all of the charges on the products, the total is +2. All the charges on the those are the reactants. All the charges on the reactants are equal to all the charges added up on the products. I can't have charges appearing and disappearing. The next step is I need to have the same number of electrons in both of my half reactions. This is my reduction. I'm losing electrons. This is showing I'm losing 1 electron. This is my oxidation where I'm sorry, that's the oxidation. This is the reduction where I'm gaining electrons. Here I'm gaining 5 electrons. If this one's losing 1, this one can't gain 5. It has to be the same number. I have to have 5 lost and 5 gained, or 10 lost and 10 gained. So I'm looking for the least common multiple of 5 and 1, which is 5. So I'm going to multiply this equation by 5, all the coefficients. So 5 iron 2s and 5 iron 3s and 5 electrons. I want to end up with the same number of electrons here and here, so that when I add the two equations together, those electrons disappear. So when I add these together, now the electrons disappear. So now I'm going to add these two together. So the 5 electrons canceled out. And it can be helpful to look and see if there's anything else that's going to cancel out. I don't see anything else. The order that you put these in, we're going to have 3 different reactants now. The order you put them in doesn't really matter. And the order that you put the products in doesn't really matter. I tend to kind of just copy the way it was given to me. That's a good question. So I multiplied this by 5. Do I have to multiply the other by 5? No.
And then the electrons. So however many electrons you add to one of them?
I need the number of electrons lost by one to be the same as the number of electrons gained by the other. Yep. So I'm just going to choose to follow this same order up here. And so I've got 5 iron 2 ions, and then next it gave me the permanganate ion, and then the other thing that I have in here is hydrogen ion, and then on the product side I have 5 Fe3 ions and 1 manganese and 4 water molecules. And then verify, you go through and make sure that the total of the charges is equal on both sides and that you have the correct equal numbers of irons and manganeses and oxygens and hydrogens.
You're recording this, right?
I am recording this, yes. Yeah. Do another one. Again, in acidic solution. So here we've got copper and nitrate, and we're getting a copper ion and nitrogen dioxide. So first we're going to break it into 2 half reactions. So I'm going to pick the reactant and product that look the most alike. So that will be the copper and the copper ion, and the nitrate ion. I didn't leave enough room. It's helpful if you line up the arrows later when you add them. So we'll break it into 2 pieces. One of these is oxidation, one's reduction. We could identify it. Do we have to? No, we can do it without identifying it. Break it into half reactions. Balance each half reaction for mass, the atoms. So here, 1 copper, done. This one, I've got 1 nitrogen and 1 nitrogen, so that's okay. And then I have 3 oxygens and 2 oxygens. And there is no way I can balance this with just coefficients. Because if I put a 3 here and a 2 there, then I mess up the nitrogens. So I'm going to balance the oxygens using water. It's an aqueous solution, water is present. So 3 oxygens and 2 oxygens, if I put a water molecule here, now I've got 3 oxygens on each side.
Should you use like the subscripts on the outside and do like 2 on the left?
So I can't change any subscripts because that changes formulas. So now I've got nitrogen and oxygen balance, but I introduced hydrogen and I have to fix that. So H2, I have 2 H's there. And so I'll balance that by putting 2 hydrogen ions over here. And we use hydrogen ions because this is in acidic solution. There are hydrogen ions floating around. So all the letters are balanced, right? And now we balance charges. So the first one, I've got 0 on the left and +2 on the right. So if I add 2 electrons on the right, then I'll have +2 and -2. This adds up to 0, and that's 0. Down here, I have 0 on the right side, and I have +2 and a -1 on the left. So that's a total of +1. So if I add an electron here, then I have -1, +1, +1, and -1 adds up to 0. So this oxidation is loss of electrons. So this is losing 2 electrons, but this one's only gaining 1 electron. So this reaction must be happening twice as much. So I'm going to double everything, all the coefficients. So 2 electrons, and that makes 4 of those, and 2 of these, and 2 of these, and 2 of those. I'm doubling it because the first reaction was losing 2 electrons. I need the second reaction to gain 2 electrons because the 2 electrons have to go somewhere. When I add this up, I shouldn't have any electrons showing up in my final reaction.
Is it different to write H2 plus instead of 2H?
It is different to write H2 plus as opposed to H2H plus. Because there is no H2 plus in Chem 1A. It actually can exist, but we have hydrogen ions, and we have 2 of them. And you might say, well, why don't we balance it and just put H2? Well, that would balance the hydrogens. But we don't know if there's hydrogen gas as a reactant here. We're only adding stuff in that we know exists in an acidic aqueous solution. So that's water and hydrogen ions. So I got my electrons to be equal, and now I can add these together. I lost 2 electrons there and gained them back here. They got transferred. So I've got solid copper, and I'm going to have 2 nitrate ions and 4 hydrogen ions. And that's going to form 1 copper ion and 2 nitrogen dioxide molecules, and 2 water molecules. Questions? Well, what if the solution is basic? There's an excess of sodium, there's an excess of hydroxide instead of an excess of hydrogen ions. So we're going to do the same process. We're just going to add one step. So when we're balancing each of the half reactions, we're going to balance the elements other than hydrogen and oxygen. We'll balance the oxygen adding water, balance the hydrogen adding H+. That's all the same. And here's the one extra step. We're going to add an equal number of hydroxide ions to both sides of the equation, because when you have H+ and OH-, they neutralize to water. So we're going to pretend it's acidic, and then once we've got it mostly balanced, then we'll fix that and make it basic. So balance the redox reaction in basic solution. So again, I need 2 half reactions. So I've got I-, and that is becoming I2. And I've got the MnO4-, and I've got MnO2. I'm going to balance for mass. The top one, I've got 2 iodines on this side and only 1 over here, so I can fix that by putting a coefficient of 2 over here. Down here I have 1 manganese and 1 manganese. I have 4 oxygens and 2 oxygens. So I'm going to balance that out by adding 2 water molecules, because that gives me an extra 2 oxygens. So 2 plus 2, 4 oxygens. And then I have 4 hydrogens that I've thrown in there now. So I have to add 4 hydrogen ions over here. And if it was acidic, we'd leave that step and go on to balancing for charges. But this is a basic solution. So I'm going to add base. I'm going to add hydroxides. Here I have 4 hydrogen ions. If I add 4 hydroxide ions, what do those become? 4 water molecules. In order for this to be balanced, I have to do the same thing to both sides. So over here I have to add 4 hydroxide ions. So I added the 4 hydroxides to neutralize the hydrogen ions. I'm going to rewrite this as water.
You just changed the coefficient of water on that side, or?
Are you referring to there's 4 waters here and 2 waters here?
Yeah, can you just make that 6 times that way?
Make it 6?
Yeah, change it to 6 waters so that way there's still the same amount of oxygen and hydrogen on each side.
That won't work actually. Yeah.
Does that have to do with the charge?
It has to do with the fact that there's hydrogens and oxygens all over the place, and we've got them in these guys also.
Okay.
Yeah. So, I mean, feel free to look for another way. To my knowledge, this is the most straightforward way. So I'm going to simplify this a little bit. Instead of this mess here, I'm just going to write the 4 water molecules. What the heck? Fine. So I can go through and check, and I've got the same number of hydrogens and oxygens on both sides. It's kind of a mess though. Now I balance for charge. So this one, which is looking refreshingly simple, isn't it? Here I have 2 negative charges on the left and a 0 on the right. So I'll add 2 electrons to my product here. So that the charges are the same. In the bottom half reaction, on this right side, I have -4, and over here I have -1. So then I need 3 electrons to make that one equal. And then I have to get the numbers of electrons the same. I've got one releasing 2 electrons and the other gaining 3 electrons. So the least common multiple is 6. And so I'm going to have to multiply the top equation by 3 and the bottom equation by 2. So this one's times 3 and this one's times 2. And it's a good idea to actually write it out, because otherwise as you're multiplying you forget what you're doing. Just check the old videos, I've done that a million times. So the top one, I'm multiplying by 3. So this becomes 6, and this is 3, and this becomes 6. Multiplying the bottom reaction by 2, so 2 times 3 is 6, and 4 times 2 is 8, and 2, and 2, and multiplied by 2 is 4, and that becomes 8. And now I'm going to put them together. The electrons are going to cancel out. I've got 6 electrons and 6 electrons. And I'm going to write down everything else. So I've got 6 I minus aqueous and 2 MnO4 minus aqueous and 8 waters. And that's going to make 3 I2s and 2 MnO2. That's not a 2, that's a 4. And 4 water molecules and 8 hydroxide ions. And when it doesn't fit on one line, you just kind of have to go down to the next line. Is there any simplifying I could do here? Is there anything that's showing up on both sides? The water. So I have 8 water molecules in the reactants, and I have 4 water molecules in the products. So if I subtract 4 waters from both sides, I can get rid of these 4 and change this 8 to a 4. And there's the balanced equation. Right? Fun.
I'm going back like 10 steps. I'm getting lost where you're adding 4 water molecules on the left side. I get like you would add 4 hydroxides to balance.
Yeah, so I added 4 hydroxides because I had 4 hydrogen ions. And those neutralize each other and form 4 water molecules.
Possible to explain that
Yeah.
in more depth? I'm not.
So I had 4 hydrogen ions, but the solution is not acidic. And so the directions told me to add an equal number of hydroxide ions. So I did. If I have 4 hydrogen ions and 4 hydroxide ions, those will react with each other. It's that acid-base neutralization net ionic equation. So 1 hydrogen ion and 1 hydroxide ion will get together and make a water molecule. So then 4 hydrogens and 4 hydroxides will react and form 4 water molecules. Okay? No, I don't add them together to get 8. So if I have 4 left shoes and 4 right shoes, do I have 8 pairs of shoes? No. Same idea. This takes one of those and one of these. And so from 4 of these and 4 of those, I can make 4 pairs. We can play with models later if you want. Any other questions? I think this is the last, yeah, it's the last one. One more, just one more. Balance the redox reaction in basic solution. Break it into 2 half reactions. Well, there's the ClO minus, aqueous, and that looks like it should pair up with the Cl minus on the other side. And then I've got CrOH4 minus and CrO4 2 minus. I'm just picking the reactant and product that look the most alike, that have the most common elements. So I'm going to put the 2 chlorine ones together and the 2 chromium ones together. Then I balance each of them separately with respect to mass. Balance everything but oxygen and hydrogen. So I look at chlorines first, 1 chlorine and 1 chlorine, that's good. I have an oxygen here, and so I have to add something in here to add some oxygens, and so I add water, because this is occurring in water. So there's an oxygen, and now I have 1 oxygen. And that adds in hydrogens. And so we balance the hydrogens by adding hydrogen ions, 2 hydrogen ions. If this said acidic solution, I could move on to the next thing, but this is basic solution, so I have to add one more step. Wherever I have hydrogen ions, I have to add hydroxide ions. This is balanced with respect to mass, but the kind of solution is wrong. So to get rid of these hydrogen ions, I'm going to add 2 hydroxide ions. For in a basic solution. If I just add the hydroxide ions over there, now I've screwed up the mass balance. So I have to add it to both sides. So I add the 2 hydroxide ions to both sides. it's mass balanced. We can simplify this, combine these, and make 2 water molecules. I think in the long run, it's simpler to take care of these little simplifications as we go along rather than trying to deal with all of them at the end. So 2 hydroxide ions and 2 hydrogen ions would make 2 water molecules.
So then by that logic, you can add 2OH to the H2O.
No, I can't add 2OH to H2O because those won't do anything.
You get what I'm saying, right?
They are together, but they don't react to form anything. Yeah.
Reason why we're adding so a basic solution doesn't dissolve.
Well, a basic solution doesn't have hydrogen ions. It has hydroxide ions. And so if we write this with hydrogen ions, where did those come from? This is a basic solution. There aren't any hydrogen ions floating around. But it's easier to balance the hydrogens and oxygens when you just add hydrogens. So we get it all balanced, and then we fix the acidic basic thing by just adding the same number of hydroxides to both sides without messing everything up. So I'm going to take this mess here and write 2H2O, because 2 hydroxides and 2 hydrogen ions would combine to form 2H2O. H2O, liquid. Is there anything else I could make a little simpler about that? I've got 2 water molecules over here, and I have 1 water molecule over there. Could I take 1 water from each side? I'm sorry. I know. This is why I hate dropping this on you, but it's in the course outline. So, is that mass balanced? Yeah, it is. It's an awfully long way to get there, but there it is. On to the next half reaction. Chromium and chromium, 4 oxygens and 4 oxygens, okay, 4 hydrogens. So I'm going to balance the hydrogens by adding 4 hydrogen ions over here. Because I have 4 hydrogens here, and so I'm going to add 4 hydrogen ions over here. I know. I'm going to fix it. So that would be great if this was acidic, but it's not, it's basic. So I have to neutralize those by adding 4 hydroxide ions. And so 4 hydrogen ions and 4 hydroxide ions make 4 water molecules. So that one's mass balanced. Now we stick electrons in there. I have -1 and -2, so 3 minus on the right side. And I have just -1 here. So if I put 2 electrons on the reactant side, I'll have -3 charge on both sides. I see these reactions like being a teeter-totter, right? And we have to balance it so it's the same amount of stuff on each side. Down here, I've got 4 negatives and 1 negative, that's 5. And over here I have 2. So I need to put in 3 electrons. You will end up adding electrons to the reactant side of one and the product side of the other. How do we know which one will be which? We could look at oxidation states and identify the oxidation and the reduction, and that would tell us, but we don't have to do that. I know to put them over here because that's the only thing I can do to get the charges to add up. If I put electrons over here, then I'm just going to have more negatives over there, and I need it to be equal. So this gives me 2 negatives and 1 negative, a total of -3, and 1 negative and 2 negatives, a total of -3. So that's how I knew where to put the electrons and how many, so that the charges balance. Not quite going for it. It's okay. Yeah, I have 2 hydroxides over here. Yeah. Let's see if I can. Oops. No. Just leave it alone. So the first one is taking 2 electrons, the first half reaction. The second half reaction is losing 3 electrons. It has to be an equal number. It's like if I give you $2, you can't have $3, right? Because where did the extra dollar come from? Thin air. Nothing comes out of thin air. So how do I make 2 into 3? Multiply by, I don't want to make it into 3, I'm sorry. How do I make a 2 into a 6? I multiply by 3. So 6, 3, 3, 3, and that becomes 6. And the bottom one I have to multiply by 2. So the 4 becomes an 8. There's a 2 in there. And a 2. And an 8. And a 6. Can you say that again?
So if you added 2 electrons connected to the first equation and 2 electrons to the second equation, does that cancel out?
Yeah, if the reaction came out so that this was 2 electrons and that was 2 electrons,
Yeah.
I wouldn't have to do anything. I could just add them together and I'd be good.
Don't.
Yeah. I'm just trying to get the number of electrons equal. So when I add these together then, those 6 electrons and these 6 electrons go away. There aren't any electrons that were brought in from outside, and there aren't any left over. They were transferred from one thing to another. So this one's even messier. I'm just going to copy down everything so that we can see what we've got, and then we'll worry about trying to make it more simple. 3 H2O liquid and 8 hydroxides and 3 hypochlorite ions and 2 of those complex ions. 2 chromate ions and 3 chloride ions and 8 water molecules. Oh, and I forgot these guys up here. And the 6 hydroxides up there. Did I miss anybody? You can see how it would be really easy to make a little tiny mistake, right? I've got 8 hydroxides on this side and 6 hydroxides on that side. So if I subtract 6 hydroxides from both 6 and subtract 6, that gives me 2 over here, 2 hydroxides. I have 3 water molecules and 8 water molecules. I can subtract 3 water molecules from each side. Minus 3 gives me 5. Yay! So now for a little bit of good news. Is this a super important part of passing Chem 1A? No. No, it's not. We'll leave it at that.